नहीं, आज वो क्लास में नहीं था। बट डबल सीओसी मिलेगा।
Hello, audible? Yes, please. Hello, audible?
Yes, sir, audible.
Yeah, great. We continue yesterday's numerical. Part 1 we solved. Now we come to the part 2. Okay. Second part and third part. Okay. Voltage regulation for a power factor 0.7 lagging and leading. So suppose here. Second part. Voltage regulation of transformer at 0.7 lagging power factor, and here we write leading power factor at 0.7 leading power factor. Okay. Here this. Okay, voltage. Now, as yesterday explained, here test data is given. So first we calculate the equivalent circuit parameters as refers to primary side. Why primary side? Because tests are conducted on HV side, no load and short circuit. Okay, like we supply the voltage on primary. So here, as I told, copper losses under short circuit. So from short circuit input power, that is considered as a copper loss. That is I1 R01, I1 square R01 total equivalent equals to how much it is? That give you 525, no? 525 watt. Okay. Therefore, R01 we can write, that is divide by I1 means 15.5 current, no? What is the current under short circuit? This is the current. Sorry. And you know, when your secondary is full load means primary is also, it show that it is a full load current. Okay. So if we take the full load current as in primary, then it gives this much loss. So see, what value you got here? 525 divided by 15.5. So this comes 2.185 ohm. Okay. Then we calculate, now from open circuit, again from this short circuit. Okay. Hello. This voltage is given and current is given total. Okay. So we can calculate total equivalent impedance. Total equivalent impedance. This is total equivalent resistance. Okay, as referred to primary side. This is also now Z01 as referred to primary side. Here we write. This applied voltage by ISC input current, VSC under short circuit, because in under short circuit condition is current is given. What is your this? It is 124. No? What voltage we apply here? 124 volt, 15.3 ampere current will flow. So this divided by IS is 15.5. Sorry, 15.3. Okay, sorry. It is current is 15.3. 15.3. Sorry, this also then change. This is 3. Okay. This is also 3. Then this value will also change. 15.3 all square. Okay, now it is wrong. 15.3, this value come 2.24. 243 you can write at home. Sorry, home. And this is 124 divided by 15.3. It comes 8.104. Then we can calculate reactance. Total equivalent reactance as referred to primary side. So Z01 square minus R01 whole square. 8.104 whole square minus 2.243 whole square. So this will come 7. Okay, so we get this equivalent circuit parameters. Correct. Now we know the current as a primary side current, you know, it is 15.3 amperes. Now as lagging power factor, your cos phi power factor is given. Okay. Either one you take the like cos phi, that is 0.7 lagging. Then phi 2 equals to, hello, shift cos inverse 0.7. What is the angle come? 45.57. Then sin phi 2 or phi 1 equivalent power factor. Okay. Sine of this point this much value. Okay. Now okay. Please. Now as we drawn a circuit, this is your what is the equation direct now? Already yesterday we discussed, na? Hello. This equation we write here, voltage regulation. It is at unity power factor. This is at lagging power factor. Now for leading power factor, it is as referred to primary side is this, and this is the primary side. At leading power factor, this sign is come negative. Okay. So this V1 minus V2 days. So we calculate V1. Directly you can calculate voltage regulation. Okay. Correct. See, this is your I1 R01 cos phi 2 plus I1 X01 sin phi 2. Okay. Therefore, percentage voltage regulation, that is lagging for I1 R01 cos phi 2 plus I1 X01 sin phi 2 divided by V1. V1 means no load voltage, okay, into 100. Correct? So you know this I1 is 15.3 into R01 is, please remember, R01 is 2.24 cos phi is 0.7 plus 15.3 into X01 is 7.788 into 0.71. They were cos sin phi 2 4.1, okay. This, okay, divide by this value come, V1 is your what is the no load voltage, rated voltage, your transformer rating. Hello, this is your primary is 3300. This is your secondary, okay, 410. With respect to primary side, you write here 3300 volt, okay. Now please 15.3 into 2.24 into 0.7. My dear, this part is come 23.99 plus this next portion is 15.3 into 7.788 into 0.714. It comes 85.077. Okay. Divide by, as a percentage, you multiple with 100. 3.99 divided by 3300, 33 only. My dear, it comes 3.305%. This is your voltage regulation, percentage voltage regulation, okay. Next, at leading power factor, here, this side we calculate at leading power factor. Same thing is there only. So this percentage voltage regulation at leading power factor means cos phi 2 0.7 leading. So at leading power factor, phi 2 is, actually phi 2 is come negative angle 45.5. What is the value? See, leading power factor means angle is negative, okay, 5.7. Then in if you calculate na sin phi 2 will be minus 0.71, negative value will come, okay. That's why voltage regulation, percentage voltage regulation is I1 R01 cos phi 2 minus I1 X01 so sine phi 2 divide by again V1. Here already you calculate na these things. Hello, these values are same, only sign is negative. So you can write na same value. Hello, you put here same values. So only this sign is negative here. So means it is 23.99 minus 85.77 divide by and the percentage के लिए you have to multiple with 100 for percentage. Now 23.99 minus 85.077 divide by, my dear, it comes minus 1.85%. Please remember, voltage regulation at leading power factor is negative. If we discuss na power factor, see, voltage regulation.
सर साइन फाई 2 आपका वो नहीं है, माइनस नहीं है, तो उसका माइनस कंसीडर नहीं करना, वो फॉर्मूले में पहले इंक्लूड है.
फॉर्मूला है तभी तो वो नेगेटिव हुआ, इसलिए है.
अच्छा,
ओके, इट इज ऑलरेडी नेगेटिव इट. तो परसेंटेज वोल्टेज रेगुलेशन, if we talk about this regulation, 8 unity power factor and lagging power factor, it is positive, and lagging power it is higher, positive and higher. Okay, and 8 leading power factor, this has a and maximum at leading, this maximum at lagging power factor also, and minimum at unity power factor. Okay, and leading power factor, this is negative, voltage regulation is negative. Okay, it means due to capacitive. Leading power factor means when we connect here transformer secondary at a capacitor load. So due to capacitance, the terminal voltage is increased. You know, in transmission line, in your engineering course, you have studied Farent effect. What is the Farent effect? In extra high transmission, long transmission lines, due to shunt capacitance, line capacitance, due to line shunt capacitance, this receiving end voltage is greater than the sending end voltage. That is called as a Farent effect. So it is means line regulation is also positive in that case. Okay, so it is negative, means this voltage is large. Okay, so now in the third part, what he asked, hello, if we write here third part, he asked the terminal voltage, secondary terminal voltage at leading power factor and lagging power factor both. Please, for this, just you draw the diagram of transformer. Okay, correct. So here, you know, here you apply V1, correct, and you know there is a equivalent impedance is there. Due to that impedance, there is a drop in the voltage. Now here you apply the load at full load. This terminal voltage is V2, and this is induced voltage is E2 here. Now this difference is due to drop, correct? No? Drop in terminal. So now he said that what is the, he asked, secondary terminal voltage corresponding to this, if there is a voltage drop. Okay, so please, Actually, that this voltage are given here. This V1 is given 3300 rated voltage. Suppose it is no load voltage. Here it is 415 volt. Then what is the V2? It means then, or either you write here, see, in equivalent circuit, if we as refer to secondary side, due to this secondary side, this is your, this is here is magnetizing branch, suppose. Okay, so here is your load terminal V2. Here it is E2 equals to E1 dash. Then due to this R0 to X02, there is a drop in this impedance. Then if you apply here, this is your total impedance Z02. So if you apply KVL, that E2, E2 minus I2 Z02, total impedance, drop in impedance. Then it is suppose positive, this is negative at an instant of time. This is positive, this is negative. So this is V2 equals to 0 by KVL. Therefore, he asked B2. Then you can write now B2 equals to E2 minus I2 Z02. That Z02 is your drop. Okay. And in voltage regulation, actually we calculate this is the drop, percentage drop with respect to your this terminal voltage. If there is, this is 415 volt, then what is the V2 after this percentage drop? So here if you calculate V2 means E2 minus E2 of into percentage voltage regulation. Means you subtract the percentage drop. Actually, voltage regulation is nothing but it is the percentage voltage drop. Okay. So that means it is 415 minus this is 415 into percentage drop is this much means 0.03305. You can write. It is percentage. Then in per unit divide by 100, it means this. Okay. Or you can just write E2 into 1 minus. You can also prepare this formula E2 into 1 minus this voltage regulation in per unit. Okay. This will give you direct, like here if you write now here you can take a this common as a 415. So for easy calculation, just you put like 0.03305. This much. This will give you direct. Hello. So if you calculate now 1 minus 0.03305 into 415. So it comes 401.28. Means after this much drop, what is the exact here? What is the terminal voltage? This. Therefore, this no load voltage we put like a 433. That is so that we get here 415 volt. Okay. Like this. To regulate by tap changer, so that now at this is at lagging power factor. Means this if at leading power factor means this is your voltage regulation. In that case, E2. Sorry, directly you can write V2. We calculate V2 secondary terminal voltage. Hello, this V2 equals to again same E2 into 1 minus. Now minus become plus. Okay, because it is positive, correct? This negative percentage drop means percentage, no? It is negative means positive. It becomes plus 0.185. Got it? Actually, in formula, it is V2 equals to E2 into 1 minus percent per unit voltage regulation, divided by 100. So means if negative means it become positive. My dear, it is 415 into 1.0185. Add na this. So this will give you get 422.67 volts. So see, at leading power factor, your output terminal voltage is higher than the no load terminal voltage, okay, induced voltage. Okay, dear, so this is your terminal voltage. Got it? Any doubt here, please? Okay. You have to calculate the terminal means equivalent parameters. Then you any doubt? See, when we do the no load test, in no load test, this is the parameter. Okay, we get only no load and magnetizing components in this two. But in this is your equivalent circuit. So this equivalent circuit parameters as referred to primary side, this as referred to secondary side. Okay, then approximate equivalent. Now test, like what test we do to calculate the performance of transformer on the basis of equivalent circuit, like by no load. First we measure the winding resistance, then we do the open circuit test. From open circuit test or no load test, we calculate the magnetizing branch component and core loss. From short circuit, we have to calculate the equivalent circuit impedance and reactance and copper loss. Now see, this is your no load test. From no load test, no load power factor and this two component of no load current. This is short circuit test. Here we calculate the copper loss and this equivalent parameter Z01, X01, R01, okay, and voltage regulation we can calculate. Now voltage regulation. In all the ETO question, there is a one question was asked. Describe any two method to determine the voltage regulation. So in that question, you write first to define the voltage regulation. So here today we study the voltage regulation and efficiency of transformer. Okay. So first you define the voltage regulation. You know, voltage regulation is very simple. Like here, like your no load terminal voltage minus full load terminal voltage divided by full no load or either full load. This is up and down. Generally we take a no load and divide by no load.
You can use any one, both of them. कोई भी use कर सकते हैं क्या दोनों में से?
Just here it is divided by V2. Here it is divided by E2. So actually we put a E2. E2 is constant, no load it. But load may be changed. Therefore this second one we consider. Okay. Because always load is not a ideal condition. There may be some change in load. Your regulation is at full load voltage regulation means, see, this is the formula. Please you write this. No load voltage minus full load secondary terminal voltage divided by no load voltage means E2. Okay, dear, this first one, please you note down. E2 minus V2, or you can write this E2 minus V2. E2 minus V2 by E2, okay, into 100%. Now, as refer to primary side, your equivalent circuit. Then from this vector diagram, hello, at suppose for lagging load, this component we have calculated, na? Okay, as I told you, okay, this vertical, this line. So this is R02 X, this R0, R02, I2 cos phi 2, then X02, I2 sin phi 2. As refer to secondary side, he is calculated, okay? Then see, this is your formula. As refer to secondary side, then here 0 V2 means at no load, your terminal load. You can replace this by E2. I can take a copy of this here. Hello. Please, this is your already actually these things are explained. Voltage regulation in terms of means as refers to secondary side means side. So this is E2 you can write. This is E2 minus B2 by E2. Okay. And this plus for lagging power factor, negative for leading power factor here. Okay. Got it? In as refer to, this is as refer to secondary side, this is as refer to primary side. So here you know this is V1 minus V2 days divided by V1, no load voltage, okay. And here please you correct this also. Any power factor you write phi 1 because it was overall power factor of transformer. So in here in this question, hello, here you please you write here, because if you write here I1 R1, then you write here phi 1. Okay, so here you write phi 1 overall power factor, please. Okay. Here also, this is phi 1, okay, phi 1 power factor, cos phi 1, okay, then sin phi 1, okay. Please correct this thing. Here same, as refer to primary side means you take primary side factors like I1, R01, I1, I1 X01 here, but I2 R02 cos phi 2 plus I2 X02. Got it? So here in question we use that actually because we know the R01 X01. If we know R02 X02, then we use this. Or either always you remember this. We now when you calculate R01 and X01, you can transfer into X01, X02. Because we know that your turn ratio, no? They are when we transfer from primary to secondary side, they multiple with k square. Okay, correct. It is very useful, please. Now come to the efficiency of transfer. Now transformer efficiency or motor, generator, any equipment is defined as a output by input. Now output divided by output plus losses. Here losses are total losses. Now there was a question in all DTO, different type of losses occurs in transformer. So there is a copper loss due to primary and secondary winding resistance. Then core loss, second is core loss. That core loss are consist of hysteresis and eddy current loss. So here we as refer to secondary side, please. So now we discuss the transformer efficiency. Efficiency, very important. So this transformer efficiency, we write in the losses in transformer first, losses in transformer. First is copper loss. So this copper loss are due to winding, primary and secondary winding resistance, due to primary and secondary winding and okay. So this is that is I1 square R1 plus I2 square R2, or as referred to equivalent circuit, it is like this. As referred to secondary, as referred to primary side, this is I1 square R01 total loss in single phase. Okay, now how we reduce? We use a high grade copper conductors. Now second loss is core loss, or it is called iron loss. They have consist of two losses, that is hysteresis and eddy current. You know, hysteresis loss are due to reversal, magnetization and demagnetizing. of core. So because your transformer is work in AC, and your AC is like this sinusoidal, and now this has a 50 hertz frequency. It means it is 100 times this will 100 times it is magnetized and demagnetized in 1 second. It change in 1 second. See, 50 hertz. So means suppose your magnetizing core, means transformer core. There is a BH curve loop is there. BH. So here it is H. This is your B. Flux density. This is your magnetic field intensity. So here actually B is directly proportional to H, or B equals to mu H. Mu H. Mu means mu0, mu R, absolute permeability H. So means when we apply the current, this core is magnetized initially like sharply, then it gets saturated. So when the zero, it will increase up to maximum value. So your core is magnetized here. Then when it reduce, it will reduce. Now when your current is past zero, the flux will not become zero. Then negative, this is negative, this is positive pulse. When negative, it is demagnetized further, then it start to magnetize in reverse direction. So in one cycle, it reach here like this. So this again magnetized, and this form a loop. So now this magnetized and demagnetized, it is in how many times? 50, 100 times in 1 second. So that appear as a loss, as heat. Heat loss means your core is heated due to this hysteresis loss. And this eddy current means what? Because this flux is linked with the core material also, that induce the current in the core, iron core. And due to iron core resistance, there is a I square R. This eddy current loss actually I square R loss. It is a core resistance. So to reduce this hysteresis loss, what we do? We have a laminated core. Laminated. And to reduce the hysteresis loss, we use a soft magnetic core. Soft iron core means silicon steel core we use. So laminated silicon steel core we use to reduce the iron losses. Got it? Okay, so there is a two loss, and this is called as a copper loss, this is called as a iron loss. Okay? Yes, please. Now suppose we have a transformer. So from this will be measured from short circuit test, as I told, short circuit test. And this we can calculate from no load test. Since open circuit test. So like this is your transformer, suppose. If we have a load here that has a power factor cos phi 2, load power factor, here terminal voltage is V2. Suppose at full load, this is your current I2. Okay. Here we apply the V1. Now, if we know there may be turn ratio N1, N2, and their kVA rating of transformer. Now we can to calculate this efficiency. First, we calculate at a particular load what is the kilowatt output of transformer. Hello, very simple. V2 I2 cos phi 2. This is your output kilowatt. If we know the voltage, current, and like. Now If you also know the iron losses, and we know the copper loss. That is at full load, suppose full load or rated load. Copper losses, it represent. Then total loss is iron loss plus copper loss. Correct? At full load. So therefore, efficiency output input. Now if you know the output, this efficiency we can write now. Output means V2 I2 cos phi 2 divided by plus output. You know, input equals to output plus total losses. Okay. In per unit or percentage, you multiply with 100. So this equation will give the efficiency. Okay. Now let us. Now we come to condition 4, because they ask no, in question what is the condition for maximum efficiency. Means when your transformer give the maximum. Actually, generally alternator, motors, they design when there is a full load. When there is a full load on alternator, it gives the maximum efficiency. Same like motor, when there is a rated load, full load, it gives the maximum efficiency. Okay. Now condition for maximum efficiency. Condition for maximum efficiency in distribution transformer. Generally, they are designed such that this condition is appear at some partial load, because on transformer, generally if you take an example of transformer, the load on transformer are change day night, winter summer. Correct, no? So how we design the transformer, so that if you design the transformer for full load, means it will give the maximum efficiency, means better efficiency at full load. But on transformer, average load is not always full load. In night hours, the load is decreased, so that we calculate. So please, if we differentiate, like if we differentiate, like you sleep, here it is vary with, see, power factor and terminal voltage will be fixed. Only this current is vary, load. So if we differentiate this efficiency with respect to load current, secondary load current, and set equals to 0. So if we differentiate this entire equation, set equals to 0. Very simple. Actually, it is with respect to your V. You apply the V by U method. V by U. Differentiate of V by U. Okay, with respect to X. This formula. Okay. You get a condition. Hello, what is the then condition? Means your iron losses equals to full load copper loss. Means at which load at a particular load when your iron loss become equals to copper loss. Your transformer give the maximum efficiency. So it is iron loss equals to copper losses or variable loss. Not your copper losses, okay? Means this is your condition for maximum efficiency. Now, generally, how we calculate the when this losses will equal? See, so if we calculate what is the, suppose 100 kVA is the rating of transformer, 100 kVA. So maybe that give the maximum efficiency at 80 kVA or 75 kVA. Okay. So like we can calculate the kVA load on transformer at which maximum efficiency occurs. Means transformer give the maximum efficiency. What that load? Very simple. Rated kVA. Rated means full load rating into iron loss by full load copper loss. Full load copper loss. Iron loss is, it is ratio with full load copper loss. kVA rating into this, okay? Please. Okay? Root of this. There was another question. Here, this question. So see, question number 2, with reference to the large electrical transformer, please define, state where this transformer are used. On board, we use a 3-phase delta connected transformer in a main, like your HT is 6.6 kV. In HT system, okay? In the main diesel electric propulsion we use, okay? State typical efficiency range is, it is 97 to 99%, 98%. Protective devices. So in transformer, in dry type, we monitor the winding temperature. We put the thermocouples. There is a continuously monitor the winding. And then your under voltage, overload, short circuit, merge price protection is there, differential protection. This protection you have to list out. Then describe the maintenance requirement. So in maintenance schedule, daily, weekly, daily. In the oil type, there is an additional safety. We check the oil leakage and the oil quality. But in dry type, dust is the main factor. We clean the dust because when dust is deposited on the winding, the moisture will there, then leakage current will be there. So we remove the dust, cleaning of the dust. Okay. Then continuous monitoring of your temperature sensors. Okay. What are the losses in transformer? Mention various factors that affect it. So as you know, losses, there is a two type losses. Factors are, copper loss depends on winding resistance and current. And your hysteresis eddy current loss are depends on the frequency, voltage. Okay. Now there is a numerical. At 25 kVA, this transformer, single phase, iron and full load copper loss are this. Calculate the efficiency at half load and 0.8 power factor. Okay. Here in the second B, iron losses are given. But here it is given 25 kVA. Iron loss 350. Or it is 0.35 kilowatt. Copper, full load copper loss. This full load. Always along with copper loss, the load condition is written. It is a full load copper loss. Means copper losses, okay. 400 watt. This is 300 watt, or it is in kilowatt, it is 0.4. Then now you write at half load. What is the at half load? What is the kilowatt output of transformer? Your half rated kVA. Half of that into power factor. This one. So you are at 25 by 2 into 0.8 power factor. Power factor variation means 10 kilowatt. Now iron loss will be same. Copper loss at half load. Losses will be 1/4 of full load copper loss. 1/4 into 400, so it comes only 100 watt. Means 0.1 kilowatt. And total losses is 0.35 plus 0.1. It is 0.45 kilowatt. Therefore, kilowatt input power to transformer, output plus total losses at half load. Output is kilowatt output at half load 10. Total losses are 0.45. Correct, no? Therefore, efficiency at half load output by input at half load into 100. Output is 10, input is 10.45. It comes 90.69. Okay, dear. Any doubt? So this losses and efficiency regulation, this question you can solve. Huh? So this is the efficiency. Huh? Okay. Now let us. Please you take a screenshot of this. Losses in transformer, hysteresis loss, eddy current loss, empirical formula, then copper loss. There is this two type losses in transformer. Okay, please. Here this is not a positive. This is coil. Hello. Okay. Okay. Hello. Next, condition for maximum efficiency. Audible? Hello, please.
Yes, sir.
So this is the copper loss, iron loss. Then as per primary side, it is we consider the secondary side. Then if you derivate and equals to 0, then we get a copper loss equals to iron loss for a condition for maximum efficiency. Now this is the kVA load at which your this losses are equal, means maximum efficiency. Full load into this. Got it? Now all day efficiency. Please remember. You know, for distribution transformer, because load is vary, that's why we consider the operating hours also. So all day efficiency, that is output in kilowatt hour divided by input in kilowatt hour. Okay. So ordinary or commercial efficiency is this, but your all day efficiency is this. Okay. Please remember, sometimes they ask you. Always all day efficiency less than the commercial efficiency. Okay. Now three-phase transformer. So tomorrow we discuss that three-phase transformer. Okay. Earlier there was a question for asking three-phase transformer, and please also you solve this question, additional questions. No, same like now you can try. See these questions. Hello. This transformer question. Hello, please. This we consider already. See, discuss the magnetic leakage. Already we solved a vector diagram with voltage regulation. What is the important yeah, why it is important? Yes, this week I will explain. Hello. Other question we already cover. Recent जो एग्जाम में पूछे हैं, एक ये क्वेश्चन है अभी, क्योंकि हमने ये टॉपिक करा दिया है, इसलिए इसको डिस्कस कर लेते हैं. See, hello, it is asked in your exam. Please tell me why it is important to maintain, means we, hello, in transformer performance we calculate two parameters, efficiency and voltage regulation. Okay, voltage regulation. So your voltage regulation lower value, it should be lower, as low as possible. Lower value, low values is recommended. Low values are, it is called, if lower values are good regulation, called as a good, and here higher values are considered as a better. Higher value, higher the efficiency is considered as a good performance. It is excellent, means good. Okay. So means it is why we consider a high efficiency. Now please let us, because you know, if you write the region first, we consider if your efficiency is high. Hello, higher the efficiency means very simple. It means your losses will be losses will be low. If higher efficiency, losses will be low. Losses will be low means your better performance. So your electricity will also reduce. Power loss is low, then better performance. Better performance. And low losses means there is a reduction in power consumption. Power consumption is reduced means your electricity bill is reduced. Electricity consumption means energy, your energy conservation means saving means energy saving. Energy saving means your electricity bill is reduced. Bill reduction. Okay, that is the. Now second part, if percent, you know, voltage regulation, if lower value, then VD, voltage drop, internal voltage drop is low. If internal voltage drop is low means load current will also current is reduced, lower. Okay. Higher terminal voltage means rated, like you know the motor terminal. finally your transformer is feed the motor. Suppose this is a motor. So if it feed the motor, so if here is a rated, if if low term means lower voltage regulation means here better voltage we get here, correct na, at bus bar. So if motor terminal is higher means motor draw the less current. If rated voltage, under voltage means motor draw the more current. So again, if current is low, then losses will be low. Again, same thing. Better terminal voltage means rated terminal voltage at equipment. Terminal voltage. Then equipment performance like motor performance is better. Performance losses are reduced. Okay, again. Got it? Why we recommend the lower value of voltage regulation, higher value of efficiency? Got it? Because as if lower value means here you get a rated voltage, good voltage. Then your load is at load terminal better voltage means your load current is reduced. Due to Ohm's law, why the current is flow here? Due to this voltage difference, VD, no? Okay. So if you are actually, if you calculate this load current, that is E2 minus V2 by this equivalent impedance. Correct na here maybe. So if lower voltage drop means lower the voltage drop means this is voltage regulation basically, then this current is reduced. If this low value means this current is low, then losses will reduce. Okay, got it? Now new question, all question we complete now, but additional like 3-phase and other question we also see here. Lot of questions also there. You can practice this like here. Hello, this 20 kVA. It is same like 20 kVA transformer. They give the primary resistance means R1, second R2, then leakage reactance X1, X2. So here both terminal resistance are given R1, R2, X1, X2. Now you calculate the regulation. Unity power factor, lagging, leading power factor. So my dear, first you calculate total equivalent resistance, total equivalent reactance as referred to secondary side you can take. Because turn ratio you can calculate from this. Okay, you can solve this. Please try yourself. Okay, definitely you can do it. Okay, dear. Good night.
Yeah, so now in this question, it's not mentioned if we have to do with refer to primary or secondary. So we can do any side, right?
Yeah, same value you can got.
Okay.
Generally, but you do the load side and secondary side better.
Okay.
Same here, lot of 100 kV as this question is also same like voltage regulation. Okay, please you prepared a new question. Okay, good night. See this question is like your we calculate like vector diagram. This 8 question is vector diagram. ये क्वेश्चन आने की it is possibility of this question they can ask. Okay, please prepared. Okay, आपके numbers starting में काफी थे 22 23, now they have reduced to 10 12. What is only this much is on appearing this time. or your if you require, you give the suggestion, feedback. Okay. If anything is you want to improve. Okay, good night.